Welcome to today's webinar, Modeling Industrial Burners with Converge, Unlock Efficiency and Performance, brought to you by Convergent Science. Thank you for joining us today for the 8th event of the 2025 Converge webinar series. My name is Wijeyakulasuriya and I am part of the Business Development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and hear the latest about burner and combustion modeling in Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our clients. Now it is time to introduce our speaker for today's event, Sameera Wijeyakulasuriya. Sameera Wijeyakulasuriya is a project manager at Convergent Science. He has been with the company for over 14 years, leading the internal combustion engine application support team. He is also the application owner for burners and gas turbines. He is a key resource for Converge support globally. Sameera received his PhD in mechanical engineering from Purdue University and is working at our headquarters in Madison, Wisconsin. Without any further delay, I will now pass the ball to Sameera. Thank you all.
Thank you, Mattia. So today in this webinar, we are going to talk about two very different but yet very important things about burner design. One, how do you use burner simulations to get efficient results? And the other aspect is how do you run simulations to get performance-based, high accurate simulations. So throughout the presentation, I would be talking about these two different aspects. And then I would be bringing out information as to what is the Converge advantage in both of these simulation types. For example, what are the tools available to you with Converge to solve the hard problems and the tools available to enhance simulation efficiency. And then I would be bringing out some application spotlights to show some past work with Converge on burners. And then we'll wrap up the webinar with some Q&A. Now let's first look at accurate performance-based simulations. Now, in these type of simulations, the need is accuracy. So high accuracy is whether it's the pressure, whether it's density, whether it's any other thermodynamic quantity or emissions, the flame shape, it's the accuracy. So you need to do high fidelity CFD simulations. And then you are typically, if you're interested in this, you're typically optimizing or creating designs that are currently not on the market. So you typically have more time to carry out these simulations because you're testing different scenarios. And with that, it's not just one design iteration that you're testing. You're testing out many design iterations with simulations to get to a particular optimized design. So your simulations needs to be robust. It should not crash on you when you run, and it needs to be predictive. So for both of those, robustness and predictive, so you need high accurate simulations. So when you are in this sector of simulations, you are testing new concepts, testing new designs. So oftentimes you might not have validation data, meaning you probably won't have built the test rig yet when you're simulating or when you're trying to use CFD for new design new design development. So it's very important that these simulations are predictive. It should give you correct results. Now, sometimes you might be interested in looking at fundamental validation of simulation models as well, because the whole simulation for a burner has flow, turbulence, combustion, emissions modeling, a lot of these physics comes together. You might be interested in looking at some fundamental validations of these different parts as well. And oftentimes, these are like advanced multi-physics simulations. On the screen, you're seeing a famous burner case called Prasinsta spray burner. It has like, it has been run with like spray, or like it has been run with premix like Fialenia as well. What I'm showing here is how Converge can be used to predict burner combustion like this, and it doesn't just predict the flame shapes and the processing jets. It gives you accurate results, as you can see on the bottom as well. Throughout the presentation, I will be talking about how these type of accurate CFD simulations would require advanced turbulence modeling like LES, thickened flame models, detailed chemistry, and adaptive mesh refinement. So we'll get into each of those like different features that Converge offers to give you an accurate simulation later on. Now, so that's accuracy-based simulation is one aspect, and then the efficiency-based simulation is the other aspect, which is equally important. So the priority here is speed up. So you need to run the simulation really, really fast. And oftentimes you might be willing to forego some level of accuracy to get to faster results, but still accuracy is important. The simulation designs that are currently on the market is of interest here. So you are probably troubleshooting some problem that came from testing, or like you're trying to troubleshoot an issue that came from an existing design in the market. Now, because it's actually a troubleshooting, and your customers waiting for that like troubleshoot, these are time sensitive simulations. So you need to be able to run these simulations really quick, find the solution, fix it, prototype the fix, and then test it out, and then like send it to the market really quickly. Oftentimes, rather than modifying or like coming up with new designs at here, you're trying to look at a post-predictive simulation where you are trying to look at deeper to understand more into why this issue came up and why is this design failing. Model simplifications are applied within reason to reduce simulation runtime, because if you want to run things faster, there has to be certain smart assumptions that needs to be taken, some simplifications, and that's very important. Simulations often are tailored to predict a limited scope of results. So you are not interested in flame shape, emissions, all of that. Your focus is mainly on if my flame shape is off, or if my emissions are off, and there's a hotspot appearing somewhere, and that's why the design is failing, you're typically focusing on that aspect to solve that. So you can make certain simplifications and get to fix that problem at hand. On the right-hand side, I'm showing a burner simulations, and I will come to this simulation later on as well. For example, I'm showing you now in this burner, you have the fuel air mixture coming from the bottom. So there's a fuel inlet and the air comes in from the bottom. Sometimes the flame could actually flash back under certain conditions. So for that, you typically have a flame arrestor. Now, modeling the flame arrestor in a three-dimensional way might be pretty expensive. So you can use, in Converge, you can use porous media to model this flame arrestor. So that's a simplification that you can do if you're not only interested about the porous media, you are interested in something downstream that's like braking. Now let's talk more in terms of like Converge features that are advantageous for industrial burners. Fully autonomous meshing eliminates the user meshing time, even for complex burner geometry. Some of these geometries, the flame arresters, the burner itself, could be like large and could be like pretty complex. But so because of that, the fully autonomous meshing in Converge is really, really helpful in cases. So you do not mesh at all. It's actually the code at runtime draws the mesh. Adaptive Mesh Refinement, or AMR, automatically resolves the combustor flow and propagating flames at low computational expense. So you, rather than like you trying to like sit down and draw the mesh and thinking, where should I need my mesh more? Where can I like use larger cells? Give it to AMR, and then AMR looks at the curvature of the flow variables and then automatically resolves the mesh, or like coarsen it so we can run with the optimized cell count and save on runtime. With Converge, you have access to fast steady-state solvers that works with combustion. We have a detailed chemistry solver that's pretty accurate, but sometimes if the number of like species is large, it could take time. So for that, we have all the required simplified combustion models as well. We have the eddy dissipation concept models, eddy dissipation model, FGM model, the flamelet generated manifold models. So for you to run simulations really, really fast. With Converge, you have access to conjugate heat transfer modeling that can be used to predict hotspots on the burners and aid in thermal analysis as well. For burner simulations, radiation modeling is very, very important. With Converge, you have access to a spectrum of radiation models, like the optically thin and P1 models, which are simplified models that are more efficient. Or like, on the other side of the spectrum, you have the discrete ordinance methods where it gives a lot of information, useful information, but it can be computationally expensive, but it's like more accurate. With Converge, you have access to simple RANS models and then all the way to LES models as well. And you have access to hybrid models between RANS and LES as well. Now, the video that you see on the screen actually is a bluff body stabilized burner, and propane is the fuel here. You can see how the use of LES and thickened flame model and detailed chemistry, in this case two-step chemistry, simplified chemistry, predicts the flame shape very accurately. Now, let me talk a little bit about the fast chemistry here. The SAGE detailed chemistry solver is an efficient way to solve detailed chemistry. This works even with the large mechanism. There is no limit for the species count. And detailed chemistry can accurately simulate the ignition process, the premix flame propagation, the flame flashback if there is flame flashback happening, if there is lean blowout happening, and if your chemical mechanism have all the emission species like the NOx, CO, unburned hydrocarbons, you can predict those as well. Now, not only Converge has access to detailed chemistry, I told you Converge has access to simplified combustion models as well. You would use this if you want efficient simulations where you want really quick simulations. On top of the combustion models available, Converge offers you a rich suite of chemistry tools to generate the tabulated ignition delay and laminar flame speed data, which are sometimes inputs to some of these simplified combustion models. Now, detailed chemistry is great, it is really accurate, but then where do you get the chemistry mechanisms? You're covered with Converge on that as well. We have a large database of fuel chemistry available to you. And then because of this large database of fuel chemistry, doing dual fuel combustion or fuel changeover simulations in burners is quite straightforward. On the screen, I'm showing a bluff body stabilized hydrogen burner. Hydrogen has become pretty popular in the recent times. And you can see how AMR, Adaptive Mesh Refinement, detailed chemistry, and LES is used to calculate the flame shapes, the flame propagation very, very accurately. Now let's talk about scalability. That's another advantage of Converge. It has cutting edge like HPC capabilities. We do cell-based load balancing, so when you run on hundreds or thousands of cores, your load balancing still stays really, really good. And we do dynamic load balancing. As a simulation is running, we are load balancing periodically. On the screen, I'm showing you an example of the Sandia Flame D burner. It had like 170 million cells, so it's a really refined simulation. And you can see near linear speed up until about 8,200, almost 8,200 cores. So that's kind of the strength of Converge. It's highly scalable. Another advantage with Converge is conjugate heat transfer. If you are interested in looking at metal thermal analysis, or like how the flame affects like the metal temperatures, Converge should be the tool of choice, because in one simulation you can do gas and as well as metal as well. There are possible simplifications that you can use to run simulations faster. Remember, I was talking about accurate simulation and faster simulations. If you want accuracy, you can simulate the entire metal, give all the solid properties correctly, and then as a combustion is going on, the metal temperatures would increase. If you want some simplified simulations, now again you can use maybe heat sources or simplified combustion models to get to the metal temperatures quickly. Now I'm going to talk about the fast steady state solver that you have access to with Converge. We have put a lot of resources into developing a really fast steady state solver that works with combustion. Now this is the Flame D case that you're seeing, this Flame D burner case. On the left hand, on the center, so pay attention to the left hand side of the screen. In the center, so there's 3 columns. So the second column, or the second picture in the middle, we used to have a previous steady state solver, and it used to work with detailed chemistry. And I'm showing you the temperature contours. So the flow is coming from the bottom, the flame, and the fuel and the air. It burns and it produces the flame. On the left-hand side, you have the new steady state solver. This is the under relaxation solver, we call it URS. Just by changing the solver, you can get now 2 times accuracy. 2 times speed up. Now, in both of these, we are doing detailed chemistry about 50 odd species mechanism. Now, if you take the URS solver, the new steady state solver, and use simplified chemistry, so that is a single step chemistry, the flame shape looks pretty decent, pretty accurate. You get about 25 times speed up compared to the previous steady state solver. So that's the advantage that you can get. So if you want accuracy, you can get accuracy. If you want speed up, you can get speed up with decent accuracy as well. Now, in order to talk about the accuracy and speed up thing, I plotted center line temperature. So on the center line, I extracted the temperature, and you can see the 2 steady state solvers with the detailed chemistry gives you the correct temperature profiles. Now, if you use single step chemistry, the outlet temperature, if you follow my cursor towards the end, X over D is somewhere around 60 plus, you have the correct temperature predicted, as you can see from the contours as well. Now, but getting there, the transient is not captured correctly. Because you're doing single-step chemistry, you can even see that in the contours, the temperatures are pretty high. Now you can tune your simple combustion model, the single-step chemistry, you can tune it to get closer and closer to the correct result. So you got to decide, am I going to get 25 times speed up? So this is not 25%, this is 25 times speed up. And then tune the parameters a little bit so I can get to my solution, the known solution, quicker. But if you're doing a predictive simulation, you don't know what the solution is, you do detailed chemistry. Now with single-step chemistry, you can actually, you don't get to do emissions. Now with detailed chemistry and with both previous and new, you have access to CO emissions. With single-step chemistry, you don't have access to detailed emission results. So that's another advantage of using detailed combustion. Let me quickly talk about GPU capability as well. Currently, the version that is released in Converge version 5, have access to GPU capabilities for cold flow simulations. In Converge 6, which will be out in next summer, we will have combustion capabilities with GPUs. Now, having said that, even currently with the CPU capability of Converge, with our AMR capability, with the the accurate scalability of CPUs, we are pretty competitive with the other GPU solutions available. To prove that point, let me bring up this paper that was published in 2025. So this year, April, early this year. This is not using Converge. They have given a constant mesh. So we did not use our AMR. So we wanted to reproduce this result. And they did the simulations for the Presinsta spray burner with one GPU core and 128 CPUs. For their GPU simulation, the average wall time per iteration is somewhere around 4.8 seconds. For their CPU solver, it's about 20 seconds. We used CPUs, 252 CPUs, similar kind of cell counts, similar time steps, and we were able to get below 4 seconds per iteration. So GPUs are important, but currently with Converge CPU capability, you can actually get really competitive, if not better results with CPUs. Okay. Another advantage that I touched upon previously is the multi-field library that Converge has. So with Converge, you have access to a lot of field chemistry, starting from methane to propane to hydrogen, all the way to dodecane, C12, and everything in between. Now, Convergent Science founded this computational chemistry consortium, or C3 for short, which does fundamental chemistry research. So the goal in this consortium is to find accurate field chemistry, including hydrogen, ammonia, natural gas, and methanol, which have become really important renewable fields lately. The researchers, there's a lot of research organizations that you can see here, world famous chemistry researchers. They work with this consortium to generate the chemistry, and then validate them against laminar flame speed data, ignition delays. And right now, the released version of C3 MEC version 3.5 has almost about 4,000 species and about 16,000 reactions. So with this kind of a capability, now having said that, you might think, oh, this is way too large, but you don't have to run with this large mechanism. With Converge, you have access to pick the chemistry that you want, extract the chemistry that you want for the field of your choice. So for example, from this pretty large mechanism. If you extract the hydrogen chemistry, it's just going to be 12 species and 37 reactions. And then with this kind of a capability, switching between fields with Converge is quite straightforward. NOx and CO emissions covered because you have that chemistry already involved. So you can the NOx and if you want to test some NOx and CO mitigation strategies in your burner, now you can do that with Converge. Another aspect of like burner design is to mitigate and avoid flame flashback. This is a study, and I'm going to now bring series of studies that shows different features of Converge and highlights different features of Converge and shows the capability to you as well. In this study, it shows for a methane, hydrogen, and air flame how under certain conditions, flame flashback can occur. And if you use detailed chemistry with adaptive mesh refinement, you can predict that. Now, what is the goal, importance of this? If you have a tool that can predict this, now you can come up with mitigation strategies, and you can design those mitigation strategies with an accurate tool like Converge. Here's another burner simulation that we did. This is called the Hylon burner. It's a hydrogen burner. There's two different operating conditions. One is an attached flame, one is a lifted flame. You can see with LES and detailed chemistry, Converge is able to capture the experimental flame shapes, whether it's attached or lifted, very, very accurately. Not only that, with detailed chemistry, it was able to capture the NOx trends and the magnitudes very well as well. Here's another publication that came out recently on gas flares. So what you see here is on the left, we have done the simulation with detailed chemistry as well as with eddy dissipation model. So why detailed chemistry? Accurate simulation. Now with 30% assisted air, there's always a cross flow from left to right. With 30% assisted air coming through the burner, you have a strong flame, and then EDM is also able to model that. But now when you go to limited conditions, like if you increase the amount of assisted air comes in, the flame should get blown out. Now, detailed chemistry, if you look at it here, the detailed chemistry is able to predict the flame blowout process. EDM cannot predict that. Even though you can see, even then, the flame shape is quite different and the flame is burning really poorly. So that's the advantage with Converge. You have really accurate tools if you want to do these limiting cases, and you have really efficient tools that can run really, really fast. EDM simulations run much faster than detailed chemistry simulations. Here's another hydrogen burner case that's we worked on under different core flow temperatures. So you can see on the left you have the coldest core flowing temperature. On the right you have the hottest core flowing temperature. Now the flame liftoff is different. So you can see it ignites on the right hand side really quickly, and the flame liftoff length is the shortest, whereas on the left hand side where the core flow temperature is the lowest, the flame liftoff is really high. Now you can do simulations like that with Converge. Now you can see how mesh dynamically refines the flame shapes, and then wherever you want resolution, you can pick where you want the resolution, and you don't have to sit down and mesh with Converge. Okay, one of my last slides is about flame arrestor modeling. On the left hand side, I'm showing if you want to do the flame arrestor in a three-dimensional way. Yes, you can do that with Converge. On the right hand side, I'm showing if you don't want to do it in a three-dimensional way, it's too expensive, but I want to be able to if a flame flashbacks, I want to be able to avoid the flame from going into the other side. You can use porous media coupled with heat transfer to give momentum sinks and then let the flame not go through, because there's heat transfer associated with the porous media as well. So you have these two different simulation types on either side of the spectrum that can be done with Converge. Now if you want superior performance and if you want accurate simulations, on the left hand side video, I'm going to play it again in a little bit. What you're going to see here is a flame combustion is initiated on the right hand side, and it is moving from right to left. And these channels that you see have conjugate heat transfer model. So you can't see the mesh here, but the thin metal strips that you see here are the walls of this flame arrestor, and they have computational cells inside them. So conjugate heat transfer. And when the wall temperatures are low, the flame should not go from the right hand side to the left hand side. And let's look at that. And you can see the flame starts moving, but then heat transfer dominates and it gets quenched. Now, on the right hand side, the center, you have the same 3D flame arrestor. But if you think about the scenario where the flame keeps coming and interacting with the flame arrestor, the metal is going to get hot. Now, researchers want to find out, or designers of flame arrestors want to find out, if it keep on getting hot and hotter, eventually the flame arrestor is going to stop working. What would that solid temperature be? So that's kind of a simulation that you see here. When the solid temperatures are high, in this case 1200 K, the flame does escape to the left hand side. So you can figure out at what point, after how many thousands of hours of operation, does the flame arrestor fails if continuous flame is being interacting with it. So you can do high fidelity modeling with detailed chemistry, conjugate heat transfer, and AMR, or you can do fast simulations with single step chemistry, steady state, and porous media. So Converge provides you all of these tools. So here's my last slide. Let me summarize what I talked about. So we started off saying Converge can do efficient, accurate, simulations where you want to run simulations really fast. You want to look at a specific problem in the burner. Converge has the tools to do that. So you can do single-step chemistry to simplified combustion models. AMR is really important here because it's going to reduce your cell count, right? But it would actually refine where you want it and when you want it, so you have that level of accuracy as well. Converge has access to a really fast steady-state solver that works with turbulence, radiation, combustion, porous media, and liquid sprays. And with superior scalability of Converge, you can run the large burner cases on thousands of cores if you have access to it, or on Converge Horizon, which is our cloud platform, very, very efficiently. So on the other side, you have the performance type simulations that you might want to do where accuracy is of importance. So the detailed chemistry with multi-field kinetics, adaptive mesh refinement, varying time-stepping algorithms. Now you might want to run these transiently. Conjugate heat transfer comes into play, radiation, turbulence, like maybe you want to do LES with thickened flame model. And at the start of your design process, if you want to do some parametric studies and design of experiments and use machine learning kind of approaches, Converge has all of these tools built into it to cater to whatever the level of simulation fidelity that you want to go into. So with that, finally, I want to talk to you about this simulation that you see on the screen as well. So you can see this is called the Cincinnati burn. It's a published work. the video will keep on rolling back. You'll see the initially on the center burner, flame gets initialized, and then after that, based on the fluid dynamics, based on combustion chemistry, the other burners that are peripheral to it gets automatically ignited. So this is a typical example of an accuracy-based simulation. It could be expensive, but at this point, you are looking at accuracy and looking at to see what is going on in the burner, rather than like trying to run things faster. You have access to both, as I said, fast simulations versus accurate simulations with Converge. With that, I will close the talk and then open up for any questions. Thank you.